Okay, these notes are on odd, even functions, composition of functions, and inverses. Essential question are quadratic functions always even? Explain why or why not. So first we're going to start off with odd and even functions. Okay, a function is even, an even function when you plug in negative x into the function and you get the original function f back. So essentially, an example of an even function is a quadratic parabola, y equals x squared. We say that even functions have symmetry about the y-axis. About the y-axis. Because I can fold the graph in half about the y-axis, and it will match itself. Here's another example. An even function. Any x I plug in here will be squared, so it will always be positive, so you'll always get the original function back. And if I rotate this around the y-axis, fold it right in half, you can see that it's going to match itself. Okay, that's an example of an even function. An example of an odd function is when you plug in negative x into the function and you get a negative f of x. Okay, so with even function, the function stays the same. You get the original back. Versus with an odd function, every term changes signs. And this will end up having symmetry about the origin. Odd and even. Okay, so an example of symmetry about the origin, we have a function you haven't seen yet, but it looks like this. This is a cubic, x to the third power. Y equals x cubed. If I fold it once this way, our graph, the first quadrant, would end up over here, and you can see it doesn't match itself. So we have to fold it one more time. If we fold it down against the x-axis, around the x-axis, then it would match itself. So when it takes two folds, it is odd. Okay, here's it larger. Okay, again, I fold it around the y-axis. Okay, and then here's where the rest of the function is. So we don't quite match, and then I fold it down. Okay, I'm recording. Okay, then I fold it down one more time against the x-axis, and you can see it matches itself. So when it takes two folds, one around the y and one around the x, it is an odd function. So we're going to determine if it's even or odd algebraically. Example 1. Determine if the given function is even, odd, or neither, because sometimes it can be neither. Okay, our given function, f of x, is x cubed minus x. So to determine if it's even, odd, or neither, we have to plug in negative x. If we plug in negative x and we get the original function back and nothing has been changed, then it's even. If we plug in negative x and every term changes signs, it's odd. If these two scenarios don't happen, then the answer is neither. So I'm going to take my function and plug in negative x wherever there was an x. So when I'm plugging in, I always use parentheses. That saves me from messing up in a lot of instances. For instance, this is cubing, so we need to make sure we're cubing the negative as well, not just the x. So I insert a negative x wherever there is an x in the function. Now, negative x cubed. Negative x times negative x is positive x squared times another negative x is negative x cubed. And a negative, subtracting a negative, we go whittle, swiggle, and make that positive x. Now notice, originally it was positive x squared cubed. Now it's negative x cubed, so the sign was changed. Originally it was negative x, and now it is positive x. So in this case, all signs change. Every term, all signs change. Every term change signs, so therefore it is odd. Okay, example 2. Let's try another one. We'll call it g of x this time. X squared minus x. Okay, so wherever there was an x, we're going to plug in negative x. So x squared, wherever there's an x, I put parentheses and plug in negative x. So I have negative x minus a negative, wiggle, squiggle. We get, oops, squared. I forgot the squared there. Squared. Well, that changes things if there's a square, doesn't it? Oopsies. Okay, let's try that again. Negative x squared, a negative times negative would be a positive, and an x times an x would be x squared, so positive x squared. Wiggle, squiggle, we get plus x. Now originally it was positive x squared, and we keep positive x squared, so that did not change. Originally it was negative x, but this one changed. Only one changed. Only part to change. So therefore, the whole thing didn't change, and also the whole thing didn't stay the same. So the answer is this is neither odd nor even. Example 3. Let's do another one. H of x equals x squared plus 4. Once again, you replace negative x wherever there was an x. Negative x squared, parentheses are really important. Negative times a negative is a positive. X times x is x squared. So positive x squared plus 4. Originally it was x squared, we got positive x squared. Originally it was plus 4, we got plus 4. So nothing changed. We got original function. So that means when nothing changes in the original function, it is even. Okay, you can also verify by looking at graphs. Here's a couple examples. We have this graph here. If I fold this side over, it's going to match itself. When it matches itself, that is even. Now this one, when I fold the right side over, it comes out something like this. When I fold the right side over, and then when I fold it down one more time, it matches itself here when I fold it around the x-axis. So 2 folds, remember, is odd. This example, when I fold the right side over around the y-axis, I get it here. And then when I fold around the x-axis, it's going to match itself. So that's another example of odd. So you can just verify looking at graphs as well. Okay, let's move on to composition of functions. Example 4. Let f of x equal 5x minus 4 and g of x equal 3x. We're going to find f of g of negative 1. Now, the key with these is you have to start on the outside. And let's start simply. Let's just ignore the negative 1 until the end. Let's do f of g of x. Starting on the outside, f is on the outside. We have 5x minus 4. So 5, wherever there's an x, I'm going to put parentheses, minus 4. Inside the parentheses, you have to stuff in g. G was 3x. We were going to put in 3x inside those parentheses. Now use your please excuse my dear Aunt Sally. Let's multiply first. We get 15x minus 4. But we're not done. We also need to insert negative 1. So f of g we've done. Now we're going to insert negative 1. So again, wherever there's an x, we put parentheses. Inside where the x is, now we're going to insert negative 1 and simplify. Multiplying first. 15 times negative 1, we get negative 15 minus 4. So that is negative 19. And I would like you to write f of g of negative 1 equals negative 19, the whole function. Okay, trying another. Example 5. This time, let f of x equal negative x plus 1 and g of x equal x cubed. Let's find f of g of negative 2. Starting on the outside, just ignore the negative 2 for the time being. Let's start with f of g, just starting on the outside. F is on the outside. F is negative x plus 1. Okay, oops. But wherever there's an x, we're going to put parentheses. Okay, and inside that x, we're going to insert g. G is x cubed. So inside those parentheses, we insert x cubed. So we get negative x cubed plus 1. But we're not done. We have to insert in negative 2 as well. So f of g of negative 2. So wherever there was an x, we put parentheses. Notice that cubed is outside the parentheses. That's very important. And where the x used to be, we're going to insert in negative 2. So following, please excuse my dear Aunt Sally, you need to do exponents first. Negative 2 cubed. Negative 2 times negative 2 is positive 4. Times negative 2 is negative 8. But there's a negative sign outside as well. A negative 8 plus 1. When we have minus and negative, we get wiggle, squiggle. Positive 8 plus 1 is 9. So please write this at the beginning. F of g of negative 2 equals 9. Okay, one more composition of functions. Example 6. Let f of x equal 2x and g of x equal x plus 4. Find g of f of 3. Careful. This time, who's first? G is first. Okay, so we're going to start finding g of f of x, just ignoring the 3 until the end. G is first, so this time we use x plus 4. Wherever there's an x, I put parentheses plus 4. And inside the parentheses, I'm going to insert in f. F was 2x. So I get 2x plus 4. Now it's time to insert in the 3. G of f of 3. 2 times parentheses plus 4. Wherever there is an x, you put parentheses. Inside the parentheses, this time we're going to put in 3. And we get 6 plus 4. 6 plus 4 is 10. Please don't just write 10. Write g of f of 3 equals 10. This is composition of functions. Composition of functions is useful for our last piece today, which is inverse functions. Okay, inverse functions. Inverse functions, which is notated by a little f raised to the negative 1. Inverse functions is the relation formed when x and y switch places. Now sometimes the inverse function may not actually be a function. Sometimes it may not be a function. The original is a function, but the inverse might not be a function. We can tell if it's not a function by the vertical line test. Each x can only have one y. Okay, the steps are pretty simple. Okay, step 1, if there's an f of x, we're going to change the f of x to y. But if it's already y, we're good to go. Replace f of x with y. Second step, switch x and y. Third step, solve for y. And fourth step, replace y with f negative 1. That means the f inverse, or the inverse function. Now, on points, if I had a relationship of a bunch of points, the inverse just means the x's and y's are switching. So switching x's and y's, the inverse relation is just, instead of 1, 2, it becomes 2, 1. See how easy that is? 3, 4 becomes 4, 3. 5, 6 becomes 6, 5. So on the graph even, the x's and the y's are literally switching places. Okay? But if we're doing it with a function, we're going to follow these steps listed right here. Find the inverse of f of x, which equals 3x minus 1. Okay? Step 1. Replace f of x with y. We have y equals 3x minus 1. Step 2. Switch x and y. So instead of y, I'm going to put x equals 3. Instead of x, I'm going to put y minus 1. Step 3. Solve for y. So now I use my inverse operations to solve for y, which means I'm going to add 1 to both sides. So I get x plus 1 equals 3y. Y is not by itself yet, so I'm going to divide by 3 on both sides. So I have y equals x plus 1 over 3. Step 4, instead of y, we're going to replace it with f inverse, or f to the negative 1. And I like to see f to the negative 1 written first. So I'm just going to change the order, put that on the left, and put the x plus 1 over 3 on the right. So that was step 4. See? Simple. And you can see on the graph, I've already graphed these ones, there's the original, here's the inverse, and if you graph it, x's and y's, here's the original, x's and y's just switch places, so it does change the graph. Okay, let's do another one. Example 9, f of x equals 1/4 x plus 2. Again, step 1. Change the f of x to y equals 1/4 x plus 2. Switch x and y's. Instead of the y, I put x equals 1/4. Instead of the x, I put y plus 2. Make sure you switch both of them. For some reason, some people accidentally only switch one, and then you have two x's. We don't want just two x's. We want an x and a y. Now we solve for y. Inverse operations, so minus 2 minus 2. X minus 2 equals 1/4 y. Now here's the trick to get rid of a fraction 1/4. We're going to times by positive 4. But make sure you times everything. You have to use parentheses. Times by positive 4, because a 4 on top cancels with a 4 on bottom. And so we have y equals. Now make sure you times everything, because this needs to be distributed in. 4 times x is 4x. 4 times negative 2 is negative 8. Last step, and I didn't write the 2, then we solve. That's step 3. So step 4 is to change the y to inverse f. And I like to see that on the left. That's just how I like to see it. So I'm just going to write it like that. Okay, simple, huh? The very last thing we're doing today is to verify that f and g are inverses of each other. You have to use composition of functions to do this. To verify f and g are inverses of each other, it's really simple. You need to make sure that f of g of x equals x and g of f of x equals x. If we get that on both sides, then they are inverses of each other. I think I'm on example 10. I've forgotten. We'll just go with example 10. Let f of x equal 2x minus 1 and g of x equal x plus 1 over 2. We're going to verify that f and g are inverses of each other. So we need to do some composition of functions. First, we're going to do f of g. Again, f is on the outside, so we're going to take f to wherever there's an x, we put parentheses minus 1. Inside the parentheses, we're going to insert in g. G is this fraction over here, x plus 1 over 2. Look how nice this becomes. 2 times the on top divided by 2 on the bottom cancels out. And we get x plus 1 minus 1. Look what also cancels. 1 minus 1, cancel, cancel. And we get f of g of x equals x. So far so good, but you can't stop there. You have to do it the other way. We're going to reverse it. G on the outside with f on the inside. Starting with g, I put parentheses where there was an x, plus 1 over 2. Inside the parentheses, I entered in f. F was 2x minus 1. Okay, this time I have a little work to do on the top. I'm going to drop those parentheses. Negative 1 plus 1 cancels to 0. And I'm left with 2x divided by 2. 2 divided by 2 cancels to 1, leaving me with g of f of x equals x. So since they both, remember this and, they both have to equal x, then that means g is an inverse of f and f is an inverse of g. It goes both ways. F is an inverse of g and g is an inverse of f. So we're going to say yes, f and g are inverses of each other since f of g of x equals x and is important, g of f of x equals x. That's how you check if they are inverses. You use your knowledge of composition of functions. Okay, so your homework, I'll be giving you a worksheet like this that's on inverse functions, finding inverses. Remember, this is easy. You just switch x and y. And symmetry on odds and even functions.